Hi folks, well we're continuing on with our discussion of basic hydraulics, and I'll begin by defining static pressure, which is the pressure at a point in an irrigation system where there is no water movement. So at that point the valve would be closed, any sprinklers or emitters on the system would not be in operation, so the water is simply not moving. And in this case it's only the vertical height of the water in the system that's really important. As we start talking about dynamic pressure and flow, other things will become important, but in this case it's only the vertical height of the water in the system that matters. So I really want you to be focused on elevation. Elevation, elevation, elevation here with static pressure. So let's have a look at an example. In this case, imagine that these are pipes and that we are viewing them in cross-section. And all we're doing here is trying to consider the relative differences in static pressure. So static pressure at points of equal elevation, like A and B here, the static pressure is going to be the same at A as it is at B. But when you start bringing elevation into the picture, what's going to happen? Let's consider C and D. Here, C is lower in elevation than D. So because of the effects of elevation and gravity, the pressure is going to be higher at C than it is at D, the static pressure. And it's just the opposite here with E and F. Since E is higher than F, and since F is being influenced by elevation change in gravity, the pressure at F is going to be higher than the pressure at E. Again, we're talking about static pressure here. Now in this example, again we're looking at pipes in cross-section and considering the relative static pressure differences at points A, B, C, and D. So points A and B are at the same elevation just as they were in the previous example, and we know that the static pressure at A is 50 psi. So since these are equal in elevation, the static pressure at B would also be 50 psi. But moving on, C is lower than B, so the pressure at C is going to be higher than B, something higher than 50 psi. Now we can't determine exactly what that is without elevation information, but the pressure at C is definitely going to be higher than the pressure at B. Moving on, D is higher than C, but lower than B. So relatively, the pressure at D is going to be somewhere in between the pressure at C and B. Now for irrigation systems, it's important to know about elevation changes because of the effects that it has on the pressure in the system. Now we're going to work through some other examples of static pressure calculations. Alright, remember from our last presentation or lecture that 1 foot of water creates 0.433 psi in pressure. And that was one of the water facts that we discussed. In this example, this is a 100-foot high water column. The P here is a symbol to indicate a pressure gauge at the bottom. So what would the reading on the pressure gauge be in psi? How would we work that out? Let's go through this example. So because we know that there is 0.433 psi for every foot of head, and we see here that there are 100 feet of head here, P would be determined by multiplying 100 feet times 0.433 psi per foot, giving us a value of 43.3 psi. Let's look at another example now. For this one, you do kind of the reverse of the last example. So in this case, you're given the pressure reading at the base, in this case 60 psi, and the question is how high is this water column, or how many feet of head do there have to be to get a reading of 60 psi. So we know, again, based on one of the constants that you had from the last lecture, that there are 2.31 feet for every 1 pound per square inch of pressure. So for 60 psi, as we have here, you would multiply 60 psi times 2.31 feet per psi, and you would get a value of 138.6 feet. Now let's consider a really common situation in irrigation where irrigation pipes might be installed parallel to a slope. The pipe might start at the water meter here, indicated by M, and be installed up to the top of the slope, and in this case we see that the elevation difference from meter to valve here is 40 feet. The valve's closed because remember, we're just looking at static pressure, so no water is flowing. We know the static pressure at the meter is 60 psi, but what is the pressure going to be at this valve? Pressure is going to be decreasing, obviously, because you're going up in elevation. So you're going to start with 60 psi and subtract the pounds per square inch lost per foot of elevation change up to the valve. And it would look something like this. So you have the 60 psi you're starting with at the meter. You're going to subtract 40 feet in elevation change times 0.433 psi per foot of elevation change, and you end up with the answer of 42.68 psi. It's important to do this portion of the calculation first before you subtract it from 60 psi. Backing up just a moment, I want to make sure that you understand what some of the symbols you're starting to see stand for. I mentioned that the M is very commonly used. M in a box is very commonly used to stand for meter. Another very commonly used symbol is this one for valve, where you have a partially shaded circle, just to orient you a little bit. Okay, now in this example, the change in elevation and the length of the pipe are both given. Which dimension would you use to calculate the pressure at the bottom of the pipe? Again, this is indicating a pressure gauge here. And what would the static pressure be at the base of this pipe? So what you would do is, again, as I said in the beginning, elevation is what we're really focused on here. So we're not even really concerned with the fact that this is 100 feet of pipe. We're concerned with the fact that the elevation change from the top of the water to the bottom of the water is 60 feet from vertical. So 60 feet times 0.433 psi per foot equals 25.98 psi. So the pressure being measured here is 25.98 psi. This example is similar to one that we've already done, except now the valve is lower than the water meter. So what's the static pressure going to be at the valve in this case? So because the valve is lower and because there is an effective elevation here, the pressure is going to be increasing. And we see over here that the elevation difference is 20 feet. So by multiplying 20 feet times 0.433 psi per foot, we end up with 8.66 psi increase in this case, because we've got the effective gravity flowing downward here, pushing downward. So the pressure at the valve is going to be 60, which is what we started with at the meter, plus this 8.66, and leaving us with 68.66 psi. Alright, here's another one. In this situation, what is the static pressure at the valve? Well, here we've got the pipe going up the hill to the valve, so there's going to be a pressure decrease due to elevation. Again, we're really focusing on elevation with static pressure. So make note here, the elevation change is 50 feet. So that pressure decrease due to that elevation change is going to be 50 times 0.433 psi per foot of elevation change, which equals 21.65 psi. So the pressure at the valve is going to be 60 psi, which is what we're starting with at the meter, minus 21.65 psi, which we've calculated here, and it's going to equal 38.35 psi. So you can see there's a pretty significant loss in pressure here. And in terms of irrigation systems, that's something that's very important to note so that you're sure you have adequate pressure to operate the system that you designed. Now, in this example, things are getting slightly more complicated, and there are several changes in elevation. So starting at the meter, which is here, where the pressure is known to be 50 psi, and working from A to B and on to C and D, and finally the valve, what is the pressure available at the valve? So let's work that out. Alright, so at A is at the same elevation as the meter, so the pressure there is going to be 50 psi, just like at the meter. Now B, we can see here, is 120 feet lower than A. So we have our original 50 psi, but we know we're also getting an increase in pressure due to this change in elevation and the drop of the pipe down to B. So we know that's a 120-foot change. So 120 feet times 0.433 psi per foot, and then adding that to 50 psi, we end up with 101.96 psi. So we've had a significant increase in pressure from A to B. Now what about from B to C? Those are at the same elevation. There's no change there. So the pressure at C is going to be the same as the pressure at B, 101.96. But then there's another slight elevation change, and you can see here that it's described as 45 feet, and it's also going up, so there's going to be some loss of pressure. And so we would take that 101.96, which is what's available here at C, and we would subtract 45 times 0.433 psi per foot and end up with 82.47 psi. So the pressure at the valve, which is at the same elevation as D, would also be 82.47 psi. So one final example. In the previous examples, the source of the water wasn't specified. You were just given a starting pressure. The difference here is that in this case, the source of water is a water tank, and the pressure at points B and C and the valve are based on the constant that 1 foot of head creates 0.433 psi change in pressure. So in this case, all the pressure in the system is being created by the pressure of that water that is elevated in the tank. So the questions are, what is the pressure at B, what is the pressure at C, and finally, what is the pressure at the valve? So at B, and I'll be going back and forth a little bit, the elevation change from the surface of the water is 120 feet, right? So at B, to get the pressure, we'd multiply 120 feet times 0.433 psi per foot for a pressure of 51.96 psi. Now, what about C? If we go back, you'll note that C and B are at the same elevation, and so the pressure is going to be the same for those two, 51.96 psi. However, there is some change as we move along to the valve, and you can see here that in addition to this 120 feet, there's another 40 feet of elevation change as we move to the valve. So we have in total from the top of that tank a change of 120 feet plus 40 feet, 160 feet in total, and multiplying that by 0.433 psi per foot, the answer, or the pressure, the static pressure at the valve would be 69.28 psi. Alright, so summing it up, static pressure is the pressure in an irrigation system when the water is not moving. And elevation change is going to determine the difference in static pressure when you're comparing them at two locations. Really, really, really important for you to note here, which is why it's highlighted in red, two constants. One, that pounds per square inch is equal to 2.31 feet of head, and that 1 foot of head is equal to 0.433 psi. It is only the vertical height of the water that determines static pressure, not the volume of water, not the shape of the container, not the size of the pipe. Static pressure is not affected by those things, or the material of the pipe, the tank, or the reservoir. So I'll leave you with some food for thought there, and we will continue with our hydraulics discussion in the next lecture.